All right, we're going to attempt a review on chapter 6 for exam 4. I've only highlighted 27 of them, but that's because most of these require calculations and not just pure memorization. So I need to give myself plenty of time. So the first one I highlighted was number 2. Keep it really simple. What's the kinetic energy of a 1.56 kilogram object moving at 94 kilometers per hour? So we're given 1.56 kilograms is the mass of the object, and the velocity is 94 kilometers per hour. Kilometers per hour. We can do better than that. There we go. Well, we know that the formula for kinetic energy is 1/2 mass times velocity squared. But if we want these units to emerge as joules, then these have to be in SI units. So the mass has to be in kilograms and velocity has to be in meters per second squared. Otherwise, we'll come out with the wrong answer. So we're good here. This is in kilograms, but this is not in meters per second. So this has to be converted. This is where your unit conversion skills come into play. This is in the denominator. So to cancel it, we have to have numerator, and down here we need either seconds or minutes, in which case we would have to chain conversions. Okay. So how many seconds are in an hour? Yep. 60 times 60. So 3,600 there, and that gets rid of hours and gives us seconds. Then we need to convert to meters. Remember early on, when you've got multiple units that need to be converted, just do one at a time. And so we're going to convert kilometers to meters, right? Denominator, numerator. So the ratio there is how many meters in a kilometer. There we go. Okay, so now, before we plug them into the formula, of course, we need to know what those units are, what the value is. So 94 divided by 3,600 times 1,000 is, let's see, 26.11. We'll keep we can round it later. Now we can calculate the kinetic energy as 1/2 times the mass, which is 1.56 kilograms. And then, oops, this is meters per second. Sorry. Kilometers, meters, seconds. We're good there. Okay, so 26.11 meters per second. That has to be squared. Okay. So I'm going to square the velocity and then times the mass and then divided by 2. And I get 1.751 joules. And since every operation in here is either multiply or divide, now we can go back to the originals. We've got 3 significant figures here, 3 there, so we need 3 here. 532 joules. Oops. Wait a minute. What did I do wrong? Kilograms. Okay, I must have made a mistake here. That was the problem. Let's try that again. 94, 3,600, and 1,000. No, it's 26.11. Maybe there's an error. Is that what you got? Okay. Maybe I made an error in the key. Oh, what's the mistake? That's joules. The kilojoules, right? So we need to move 3. Well, let's see. This would be, if this were kilojoules in standard units, we would move 3 here. 0.532 kilojoules, right? So that would be 5.32 times 10 to the minus 1 kilojoules. I was trapped by my own answer. So calculation is correct. The instructor doesn't know his units. That was 2. That was our first one. And at this rate, I'm never going to finish. All right, let's go down to 3. Which of the following statements correctly describes the signs of Q and W for the following exothermic process? Okay, we're looking, the question is, what's Q and what's W for this process? Well, the process is exothermic, right? So Q has to be negative. How about W for this process? Okay, if it's going from gas to liquid, let's draw a picture. I think pictures help a lot. If we're going from, let's see, if we start off with a gas and it goes to a liquid, what's happening to the volume? If the pressure is constant at 1 atmosphere, then what will happen to that piston if we go from a gas to a liquid? It's going to decrease, right? We decrease the volume. So work equals negative pressure times volume. Remember that? Okay. So if pressure is constant, but volume is decreasing, so final minus initial would be a negative number. The final is a smaller number than the initial, so it'd be a negative number. That'll make this negative, and that make this whole thing positive. Right, that's the mathematical way to look at it. The other way is, if the volume is decreasing, we're doing work on the system, which makes it positive. So you can look at it either way, and you get the right answer. So Q is negative and W is positive, which would be C. Okay. Or are we still thinking about it? This one's the easy part because it tells you it's exothermic. This is probably the part that will twist your brain around. All right. Let's see. Who's next? 7. Check out 7. 1 mole of an ideal gas is expanded from a volume of 1 liter to a volume of 8.93 liters against a constant external pressure of 1 atmosphere. How much work in joules is performed on the surroundings? Okay. So we're going at constant pressure, 1 atmosphere, right? And volume, the initial volume is some value and the final volume is some value. So initial volume, we start off at 1 liter to 8.93. Okay. So this is 1 liter. This is 8.93 liters. Okay. So we can calculate the amount of work that's performed by 1 atmosphere. And there's a negative. Remember, we have to put that fudge factor in there because of the nature of Q and W relative to the system. So that negative has to be there. And then final minus initial. So 8.93 minus 1 liters. So in terms of liter atmospheres, we have minus 7.93, right? Liter atmospheres. Okay, but the answers are all in joules. So we need a conversion factor, and they've given us one. We need to go from liter atmospheres to joules. And the conversion factor is 101.3 joules per liter atmosphere. Okay. So let's see, 7.93 and 101.3 is 8.03 times 10 squared. This is a negative joules. Okay. They're using standard units. Right. So this is negative 803 joules. The wording of the problem says how much work is performed on the surroundings. And negative means on the surroundings because the system is doing work on its surroundings. Work is leaving the system. So that's why it's negative. And the value is negative 803, which is why the answer is B. All right. Next one I got highlighted is number 12. Calculate the work associated with the compression of a gas from 121 liters to 80 liters at a constant pressure of 13.1. And this is in liter atmospheres. This one actually is simpler than the earlier one. So, as is customary, I want to extract information from that problem and put it in a recognizable form. The gas is going from 121 liters initial volume. Yeah, 121 liters initial down to a final volume of 80 liters under a pressure, a constant pressure of 13.1 atmospheres. Now that we've got it up here, we see the question says, what's the amount of work done? So we go to our formula, right? Minus pressure times volume. So the pressure is 13.1 atmospheres. And the volume, actually the change in volume is the correct term, is final minus initial. So we got 80 minus 121. Okay. So the value is going to be positive. This is a negative, and that value is going to be negative. So we're going to have a positive value up there. And 13.1. I get 537 liter atmospheres. So that would be B. Okay. And next highlighted one is, okay, 14 through 17 is based upon that blurb up there at the top. So what does it say? Consider a gas in a 1 liter bulb at standard temperature and pressure. Gas in a 1 liter bulb. Okay. Standard temperature and pressure. If we were doing gas problems here, it would be 0 degrees. But for all other chemistry problems, standard temperature is 25 degrees. So this is volume. Temperature is 25 degrees C, and pressure is 1 atmosphere. All right, so those are the conditions of our gas trapped in that bulb. Oh, it's connected to, sorry. It's connected to via valve to another one that's a vacuum. Pressure equals 0. Okay, now we have the problem set up. When the valve between the two bulbs is opened, what are the values of Q for this one, W, delta E. I bet the last one's delta H. Yeah, delta H. Okay. So let's tackle the problem. It's standard temperature and pressure for the entire experiment. There's no temperature change at all. All right. So that means there's no heat transfer. This is temperature is constant. Q has to be 0. Okay. Which means if there's no change in pressure, even though the volume changes, no change in pressure, that's also true. And since pressure is constant, remember, enthalpy is the same as heat, as long as pressure is constant. All right, so that one's also equal to 0. How about delta E, which is internal energy, right? It's Q plus W. So we need to know what W is. So is there any work being done? No, there's no work being done on anything because it's not pushing against a pressure. The pressure is constant at 1. Now we don't know what the volume is, so we can't calculate it anyway. So we have to say that there's no work being done, right? This is the system, right? So there's no work being done on the surroundings at all. Okay. So now we know that 0 plus 0 equals 0. So they're all 0 under these circumstances. All right. So that got rid of 4 of them in a hurry. How about 18? Of energy, work, enthalpy, and heat. Oh, that wasn't supposed to. I highlighted them. I forgot. Is it like that one? No, it's on this one. Okay, because that's okay, because this is a key. Energy, work, enthalpy, and heat. How many are state functions? So energy, well, the work, enthalpy. Well, actually, let's be consistent. Enthalpy and heat. How many are state functions? In other words, it doesn't matter what the original state was, just matters, it only matters where we're at right now. It doesn't matter how we got there. Right? This is a state. This is a state function. How about the other two? What's the magic word for them? Starts with a P. Path. It does matter for work and Q, the path that was taken to get from one place to the other. But for energy and enthalpy, it doesn't matter. All right, so how many are state functions? 2. 19. Which of the following properties is an intensive property? All right, what do we have choice? We got mass, temperature, volume, concentration, and energy. Okay, we're looking for intensive properties. Well, which one of these depends upon the amount of substance? Mass depends on the amount of substance, so it's extensive. Volume depends on the amount, so it's extensive. And energy depends on the amount. Because if we have more, say we have more moles of reactants, then we're going to get more energy. So concentration and temperature are intensive properties. And that would be, let's see, Roman numeral 2 and 4 would be C. Okay. Now, what's the difference between temperature and concentration? In terms of calculations, I should say. This is a ratio. This is not a ratio. Ratios are going to be typically intensive properties. There are only a couple of them that I can think of that are not ratios in intensive properties, and temperature is one of them. All right, 23. It's starting to get weak. Let's see if I got another one. Okay, consider this reaction. We're burning ethanol. Reaction is endothermic, exothermic. Oh, enthalpy term could be different if the water form was gaseous. Oh, okay. Well, I'm not going to write the formula up there because it's on the board. Well, it's either endothermic or exothermic. It can't be both at the same time, right? So which one is it? What sign's in front of the enthalpy? Negative. Negative in terms of the system means exothermic. Energy is leaving the system. Heat's leaving the system. So that negative tells you it's exothermic. But we've got a fly in the ointment there. Number 3, the enthalpy term would be different if the water formed was gaseous. Notice the water in this time is liquid. So when a gas goes to liquid, it gives up energy, right? So the part of the energy for that exothermic term is derived from the phase change from gas to liquid for water. So if we let water remain a gas, then the enthalpy would be a lesser value. Well, actually, it'd be a greater value because it's negative. But the number, the absolute value of the number would be smaller. It would give up less energy because it's still in the gaseous phase. So number 3 is also true. So 1 and 3 are both true. Now, why does it say, no, 2 and 3, excuse me. 2 and 3 are true. Exothermic, and it would be a different value if water were gas instead of liquid. All right. 24. Let's see, how much heat is required to raise the temperature of 5.75 gram sample of iron with that specific heat from 25 to 79.8? How much heat? All right, what's the formula? It's probably in the useful information. Should be. Let me check just to be sure. I think the only thing, the only term that I've not included in this value is Avogadro's number. We discovered that not too long ago. So you just have to memorize that one, which is what? Pop quiz. 6.022 times 10 to the 23rd is Avogadro's number. Okay, so we're looking for the formula. Should be. I don't see it. Oh, there it is, the bottom. MS delta T. So if we're trying to find the amount of heat required, it's actually I wrote it this way. In that way, it's mass first, but I wrote it this way. Specific heat times mass times the change in the temperature. So specific heat is given as 0.450. 0.450 joules per gram degree C. And what's the mass? I'm breaking my own rule. Usually I set up a table and pull that information out. But this is such a simple calculation, 5.75 grams. So that gets rid of grams. How about change in temperature? Final minus initial. 79.8 is final minus 25. There we go. And that gets rid of degree C and leaves us with joules, which is what we want. All right, so if I did my calculations right, it should be 142 joules. Close? Okay. All right, 26. Uh, 32.5 gram piece of aluminum is heated to 82.4 degrees C and dropped into a calorimeter. This is going to take some a little more diligence. Containing water, initially at 22.3 degrees. The final temperature is 24.2. Ignoring significant figures, calculate the mass of the water in the calorimeter. What else are we ignoring in this setup? The effect of the calorimeter. It's not included, so we have to ignore it, right, in order to solve the problem. All right, so let's put our values up here. Aluminum, 32.5 gram piece of aluminum. Mass of aluminum, mass of aluminum, 32.5 grams. And aluminum is at, well, let's put the heat capacity up there. Get everything on the board. 24.03. 24.03 joules per mole degree C. So this is molar specific heat or molar heat capacity. Initial temperature is 82.4 degrees. So temperature initial for aluminum is 82.4 degrees C, correct? Yeah. We drop it in the calorimeter and the water, I guess I'll put it over here so I can spread that way. The mass of the water is oh, that's the question, isn't it? Mass of the water is the question. Okay. Specific heat of the water equals 4.184 joules per gram degree C. Well, it stops at 4.18. So if I use 4.184, we're probably going to get a slightly different value. Initially at 22.3 degrees. So initial temperature here is 22.4 degrees C. And then final temperature is going to be the same for both of them, isn't it? Now, once they come to equilibrium, the final temperature is 24.2 degrees. Okay, is that everything? I think that's everything. Now we set up our problem. Remember, calorimeters are a closed system. So whatever happens in the calorimeter stays in the calorimeter, and it's always equal to 0. We're going to have a heat change for water, and we're going to have a heat change for the aluminum. And if they had given us information on the calorimeter, that would also be a term. But since it's not there, we just ignore it. All right. So this is going to be mass of the water and delta T for the water. And then the aluminum times the mass of, actually, this is molar heat capacity. So what we need is the moles of aluminum, correct? Times the change in temperature of the aluminum. So why don't we calculate the moles of aluminum while we're here? So what's the molar mass of aluminum? 26.98. 26.98. So if we do 32.5 grams and 26, let's set it up correctly. We need to get rid of grams, leave us with moles. So it's 26.98 in the denominator. Gives us so many moles. One 1.204, 1.205, 1.205 moles of aluminum. There we go. All right. So we can start filling in values here. Specific heat capacity for water. I'm going to leave the units out because I don't have enough room. Mass of the water is our unknown. How about delta T? Final minus initial. There's final minus initial. And then aluminum, 24.03 joules per mole degree C. And we have our moles, 1.20205 moles. And then delta T for aluminum is final minus initial. 24.2 is final, minus initial 82.4. There we go. That's the thinking part. The rest is number crunching. So let's see. That's going to be what? 2 degrees, right? 24.2 minus 22. Oh, no, sorry. 1.8, right? Okay. 1.8 here times 4.184 is 7.531 times the mass of water. And then this one's going to resolve itself into a number. 24.2 minus 82.4 gives us a negative number times 1.205 times 24.03. And this is negative 1685.2. That's going to be joules. And this is going to be units of joules per grain. So once we get grams in here, that goes away. But what we have to do now is put this on this side, 1685.2. Now it's positive, and this is 7.531 times the mass of water. So the mass of the water is going to be 1685 divided by 7.531. when I get 2 rounded off to 3 to 4 grams. Answers in grams. I think I got 212. Could that could have made that much difference, or did I make a calculation error? Okay. So it's very likely that I kept that value right there. So that would make this smaller. Yeah. If I made that, this value would be smaller. Divided into this value would make it. No, I should have made it smaller. The other direction. Let me see what it would be. 1.8, 4.18, right? Yep. Times. That would have been 7.52. So 7.52. Anyway.
Still the same.
Huh?
It's still the same, right?
Well, it's close.
Yeah.
Yeah. So maybe the key's wrong. That's possible. Did I put all the right values in here? 32.5, 26.98. Yep. Did I do this one right? $1.205. Yep. Okay. So that 24.2 minus 22.4. 22.3. That was my mistake right there. That should be a 7. Okay. So if we do our calculations right, it should come out to 212. That was the error. And it will be on this side also, right? 24.2 is good there. This one was wrong. That's the wrong direction, isn't it? 312 is 8. Three 12 is 9. There we go. So that makes this value bigger, makes that smaller. 950. 7.950. That's it right there.
Yeah, that one.
That would be 212, right?
Mhm.
Okay. So to save time on an exam, you set it up right, and you're just a little ways off. 212 is your best answer. All right, 27. You're on time. I'm eating up a lot of time with mistakes. If I were an artificial intelligent hologram, that wouldn't happen. Or would it? Could. It's just a program, garbage in, garbage out. 45.9 gram sample of metal is heated to 95.2 and then placed in a calorimeter. 120 grams of water, the final temperature of the waters. Okay, so we're going to use this. The unknown now is not mass of water, it's the specific heat of the metal, right? So let's just set it up and then we'll move on. So 45.9 gram sample. So the mass of the metal is 45.9 grams. This is whatever, mass of the metal. The mass of water is 120 grams. Okay. Specific heat of the metal is our unknown. Initial temperature of the metal. Heated to 95.2 degrees. Probably did it in a water bath. Specific heat of water is our usual. Let's use the one that's given here. Just 1.8 joules per gram degree C. And then the initial temperature of the water, let's see, this is the metal, this is water, is 21.6, right? 21.6 degrees C. And the final temperature is 24.5. So we set it up. And the answers are in joules per gram degree C. So we don't have to change to moles. We're working with mass only. So this is the Q of water plus the Q of the metal. Okay, Q of water is 4.18 joules per gram degree C. And mass is 120 grams. And then the change in temperature is final minus initial. Right, that's one term. Then the term for the metal is our unknown times the mass of the metal, which is 45.9 grams. And then the change in temperature, which is 24.5 minus 95.2. Okay. And once you resolve that, let's see. It should be iron, 0.45. Do we need to work it out? Or you think you can do the algebra? We're good? Okay. So this value should come out to 0.45 or very close to it. Joules per gram degree C will be iron. Things in my pocket. Now, if I change conditions, comes up some other value, then definitely will have to work it out. All right, let's see, 28. $295.5 grams of solid at 30 degrees and let it melt 425 grams of water. Water temperature decreases from 85.1 to 30. Calculate the heat of fusion of this solid. All right, we didn't talk about heat of fusion, so I need to tell you about that. If it says that the solid is going to melt, it's going to go from a solid to a liquid. So when something goes from a solid to a liquid, does it give up heat or absorb heat? It absorbs heat, right? You need to add heat to those molecules to make them leave their structure, right? Solids are structured, add heat, then they can move past one another. All right, so the heat of fusion, we often write it this way, delta H, like that, is going to be some value. And the heat of fusion is in terms of joules per, well, look at the answers, joules per gram. Okay. You'll see it different ways, joules per mole, sometimes kilojoules per gram or whatever, kilojoules per kilogram. But since our answers give us joules per gram, then we're going to go with that. That's how much heat it takes to melt a certain number of grams of the substance. That's our unknown. All right. So, and let's put the rest of the stuff up here. 295.5 grams is the mass of the solid. Right? And it goes, the solid, this is also important. Heats of fusion occur at a temperature. No temperature change whatsoever. That's why you don't see a temperature term there. It changes its phase at that temperature. And that's important. We're at the temperature of 30 degrees. So that would be the melting point of this substance. Right? So at temperature at 30 degrees. Okay. In 425 grams of water. Oh, excuse me. The water temperature starts at 85.1. So the mass of the water, okay, this is also important. The mass of the water is 425 grams. The water does have to change temperature. Its initial temperature, temperature initial is 85.1 degrees. 85.1 degrees. This is a highly hypothetical situation. Its final temperature is 30. So the temperature change does matter for the water because it's not changing phase. It's just giving up heat to this solid so that it will change its phase. And it ends up at 30 degrees. It's a practical matter that's difficult to do. All right. So we can set it up the same way. Is the heat of the solid, the heat that the solid absorbs, plus the heat of the water that's given up equals 0. Right? The Q term here is this heat of fusion times the mass. And that was given to us. The mass of the solid. Okay. The water term is the same as we've always used. 4.18 times mass time change in temperature, which is it goes to final 30 minus 85.1 degrees C. All right, so now here's our might as well put the mass in there. 295.5 grams. So our unknown now is the heat of fusion. All right, so this is 295.5 times delta H plus whatever that turns out to be. 85.1, the negative number, 425 times and 0.18 times. So this number over here is minus 97885. 1, 2, 3, 4. And delta H then is going to be this positive 97,885 divided by 295 plus 5. Which is 331 joules per gram. Well, they're all positive numbers, so 331 joules per gram is the heat of fusion. The reason that the sign doesn't matter in this case is because it's the same value whether it's freezing or melting. Right? If it's melting, of course, it's absorbing heat. And this is in terms of the water, obviously. So whatever the absolute value is, that's your value. We'll get into next semester, we'll get into more detail and phase changes. This is just a practical application. Okay. 32. In the lab, you mix two solutions. They start at the same temperature. Temperature of the resulting solution decreases. What following is true? If you mix two solutions together and the temperature decreases, what does that say about the reaction? Any reaction that takes place, if the temperature decreases, it's an endothermic process. Okay. Let's see. The chemical reaction is releasing energy? No, it's absorbing. The energy released is equal to S times M times delta T. The energy released. That's the key. It's not released, it's absorbed. Okay. So the formula is irrelevant. The terms there, the wording there is contradictory to the evidence. C, the chemical reaction is absorbing energy. That's true. And D is just the opposite, exothermic. So it's not more than one of these. It's only C is true for any of those statements. All right, 36. Exactly, 123.7 joules will raise the temperature of 10 grams of a metal from 25 to 60 degrees. What's the specific heat capacity of the metal? All right, so actually this is simpler than any of the others. If we have this relationship, SM delta T, and we know what the Q is, 123.7 joules, and that's our unknown. And the mass is 10 grams. And the delta T is, it goes from 25 to 60. So 60 is final, 25 is initial. Then this is 35, right? So both of them together is 350. And S would be 123.7 divided by 350. Which is 0.35 joules per gram degree C. Closest answer there is B. Did I lose anybody? I kind of bunched everything together to get from there to here, because I'm racing the clock. 38. On a cold winter day, a steel metal fence post feels colder than a wooden fence post of identical size because. All right. If the fence post feels colder when you touch it, and you probably don't want to touch it with your tongue or you have a place in the movie Dumb and Dumber. Dumb and Dumber? Yeah, Dumb and Dumber. So why does it feel colder than a wooden fence post of identical size? Well, if they're at the same temperature, right? They're out in the elements, exactly the same temperature. Which one has a higher heat capacity? That's the real question. Let's go back to feeling colder. Right? fence post feels colder, which means it feels like it cools your tongue or it cools your fingers more than the fence post. Right? Fence post has a higher heat capacity. Let's see. I need a better way to explain that. Let's see. This is the wood, and this is the fence post. Okay. This one has a heat capacity for wood, and this one has a heat capacity for metal. Okay. So if this is the system and we touch it where our hand is the surroundings and it feels colder, right? Our hand touches this one and it feels colder than that one. Ah, okay, I got it now. Let's see. We could explain this intuitively or mathematically. We'll try intuitive first. Okay. If this one, you have a certain amount of heat leaving your hand. If a certain amount of heat leaves your hand, the temperature here will increase more because the heat capacity is lower. If the heat capacity for this one is less than this one, then I'm going to have to use a formula. Q, let's see. Q equals heat capacity times mass times change in temperature. So if we're looking at S, we say S equals Q divided by M delta T. So if the heat capacity for the metal is less than the heat capacity for the wood, well, that's not intuitive. Okay. Okay. If the metal is lower heat capacity than the wood, that means that the temperature change for the metal is going to be greater for the same amount of heat, right? Because it has a lower heat capacity. Temperature change here is going to be greater. So delta T here is going to be greater than delta T here for the same amount of heat. So you're going to sense a greater change in temperature here than you would for that one. That's the intuitive explanation. That's probably good enough. So the specific heat capacity of steel is lower than the specific heat capacity of wood is an explanation for why this one feels colder than the wood does. Because for the same amount of heat, the temperature change is greater for this one, for the metal. And actually, there's a physical price to pay, right? If you stick your tongue to a metal post, it's going to freeze, right? Because the temperature change is greater and faster. It freezes ice on your tongue and you're stuck till somebody comes along with a cup of warm water and turns you loose. Or if your friend is dumb, they'll try to pull you loose from it and then stretch your tongue all out of shape. Jim Carrey and Jeff Daniels, right? Yeah, what a pair. Okay, consider this reaction. Oh, that's the same reaction as before. We were looking at the combustion of ethanol. All right, when 21.1 grams of ethyl alcohol is burned, how much energy is released as heat? Okay, so this one, we will need the equation. And this is liquid. These are under standard conditions. So at standard temperature and pressure, ethanol is going to be a liquid. Oxygen, of course, is going to be a gas. And we're going to produce, let's see, put carbon dioxide first, which will be a gas at standard conditions, and water under standard conditions will be liquid. And delta H for this is negative 1.37 times 10 to the third kilojoules. Okay. So this is a stoichiometry problem. We have 21.1 grams of ethyl alcohol. Right? And it doesn't say how much oxygen is there, so we have to assume it's excess. And it would be if you burn it in the atmosphere. So we're going to use up all of that. If we want to find out, that value is kilojoules per 1 mole of ethanol, kilojoules per 3 moles of oxygen, kilojoules per 2 moles of carbon dioxide, kilojoules per 3 moles of water. So if there's only 1 mole gives you that, we need to find out how many moles that is. Right? So what's the molar mass of ethanol? Let's see, 2 times 12.01, right? For the carbons. 6 hydrogens. And 1 oxygen. Add those together, 24.02 and 6.06 and 16. So that's 46.08 grams per mole. Divided into 21.1. And I get 0.458 moles. So if this value is per 1 mole of that, then we multiply it by this, minus 137 times 10 to the third kilojoules per 1 mole of ethanol. That's my abbreviation for ethanol. Okay. So if I say 1.37, did I get that right? Yeah. Exponent 3 times. That's negative 6.27 times 10 squared. It's in standard notation. No, it's in kilojoules. So 6.27, it says how much energy is released. So it doesn't have to have a sign to answer that question. We know that this says that much is released. So that's why C is the best answer. Okay, 43. And 45. All right, I'm running out of time. How many more do I have to go? 45. Ooh, that's a lot. No, it's already stated. Let me see what type of problem this is. The total volume of hydrogen gas needed to fill the Hindenburg. Is that how much energy was evolved when it burned? What you have to do is find out how many moles of hydrogen gas were in the Hindenburg, and then apply it to that equation. All right, so let's see how quick I can get that up there. 2.11 times 10 to the 8th liters. That's the volume of hydrogen gas at 1 atmosphere. And 24.7 degrees temperature, degrees C, and minus 286 kilojoules, minus 286 kilojoules equals delta H for that reaction. So how do we find out how many moles of hydrogen were in that bag? Actually, there's several bags, but have you gotten everything from chapter 5 already? Ideal gas equation. There's your moles right there. N equals PV over RT. Right. Pressure is in atmospheres, that's good. Volume is in liters. R is 0.08206 liter atmospheres per mole K. And temperature, plus 273. So we have four. Oh, excuse me. So, right. That's 7. That's 9. That's 297.7 K. That gives us how many moles? So this is per how many moles of hydrogen for 1 mole. This is per 1 mole of hydrogen. Then all we need to do is find out how many moles of hydrogen, multiply it by that. And that gives us joules. No, gives us kilojoules. Sorry, kilojoules. So that will give you the answer. And you should come out with 2.47 times 10 to the 9th kilojoules. That is a massive amount of energy. So when you go back and look at the newsreels from the Hindenburg crash, that's a good explanation for all the energy you see being released. What's amazing, the miracle, is how few people died in the accident. All right. Uh, 46. Let's see. Based on the above reaction, methane with chlorine yields carbon tetrachloride and hydrogen chloride gas. Based on that reaction, what energy change occurs when 1.2 moles of methane reacts? And we assume that the chlorine is not limiting. All right, that's simple. 1.2 moles times minus 434 kilojoules. Right. So we should get about what, 490 minus 490 minus 5. Oh, released. So 5.2 times 10 to the 5th joules. Do we need to work that one? Good. Moving on. Skip a few here. With these specific heats for the metals, if the same amount of heat is added to 25 grams of each of the metals, which are all at the same initial temperature, which metal will have the highest temperature? Okay, this is one that you can reason. Lower heat capacity means for the same amount of energy, you get a bigger change in temperature. So if they're all 25 grams of the same metal, the one that's going to change the most in temperature is the one with the lowest heat capacity, which would be lead, minus 0.127. The same amount of heat will make lead change a greater temperature. Right? When you say joules per gram degree C, and you have this as constant, and you introduce a change in temp, you introduce the same, actually, same joules, same grams. So the inverse relationship is what we're saying. So the one that changes the greatest degree of temperature, inverse is the lowest. S. Okay. That's the intuitive explanation. I'll skip these because they're all ABCs and not real chemicals. I don't use those when I have to. Given the heats of the following reaction, calculate the delta H for the reaction. All right, this uses Hess's law. So maybe I better do this one. Think. Okay. How many Hess's laws do we have? I know we got that one. Oh, there's another one. All right. Let me hold 59. We'll come back to that one. If you're still here. If you're not, I'll go ahead and do it. And get this one right here. Choose the correct equation for the standard enthalpy formation of CO, where the heats of formation, the enthalpy formation is minus 110.5. All of them have minus 110.5. Right? Every one of those choices. So we need to focus on how do you write the standard heat of formation for carbon monoxide. Okay, remember how to do that? You start with the product. Carbon monoxide is a gas under standard conditions. And we're going to make that out of carbon under standard conditions and oxygen under standard conditions. That's a gas. This is graphite. Okay. So how do you get there? Well, we only need half of that one. And we need one of these. So carbon graphite plus 1/2 oxygen yields your gas. This is a solid, excuse me. Well, actually, we called it graphite, so that's understood. That would be C. Yeah, C. Okay, that's how you construct the reaction for standard heat of formation. You start with the product and you work your way back. I didn't write the number on that one, did I? Let's see if there are any others that are worth dealing with. Oh, this should be fairly simple. One of the main advantages of hydrogen as a fuel is what? If hydrogen's the fuel, right? When you burn hydrogen, what does it react with? Oxygen. And it produces water. Right? So we need 2 here and yeah, 2 here. That's the biggest selling point for hydrogen as a fuel is the only product is water. Which of the following is not being considered as an energy source for the future? This is kind of a trick question. Ethanol, methanol, yeah, seed oil, shale oil, those are all energy containing compounds. Carbon dioxide is not. Carbon dioxide is a product of combustion, right? So it's sort of a trick question. Now, we haven't explained why that is yet, but I think we'll get into that next semester. A gas absorbs 188 joules of heat and performs 310 joules of work. The change in internal energy of the gas is, all right, when you set this one up, the signs are extremely important. So if a gas absorbs 188 joules of heat, right, 188 joules of heat, and it does 310 joules of work, that's leaving. Right? So this one's going to be a positive value, right? All right, this is Q, this is W, and internal energy is Q plus W. So Q is going to be a positive value because it's being added to. 310 is a negative value. So the overall change in internal energy is going to be negative 122 minus 122 joules would be delta E. It's helpful to draw pictures sometimes. A lot of times, as a matter of fact. Okay, this is another one. Nitric acid was first prepared. That's a lot of fluff. Calculate the delta H for this reaction. Okay, for this one, we just use heats of formation. Right, I'm over. So if you got to go, I'll get it recorded. So if we're going to do the delta H here, we need the summation of heats of formation, right, for the products minus the heats of formation of the reactants times the number of moles of each. So since there's 1 mole of each one, we can just use the values as is. Right? So what are the products? Sodium hydrogen sulfate, which would be minus 1125.5 minus 1125.5. And then the other product is HNO3, which is minus 135.1 minus 1 joules, kilojoules. And then we subtract reactants. So sodium nitrate is minus 467.8 kilojoules plus the other reactant, which is sulfuric acid. And that's minus 814. Minus 8 kilojoules. Okay. So this is going to be a positive number. This is a negative number. And delta H, once we do that calculation, should come out to 21.2. So this is an endothermic reaction.
Yeah.
The way alchemists made nitric acid. Let's see. Okay. Now I can go back to 59, and I don't mind finishing with an empty room. I've done it before. It'll be on the recording. But I want to take my time with this one, because learning how to use Hess's law is a vital technique. 59. All right. So the first thing you do when you calculate the delta H with a Hess's law as your basis of operation is you go to the finished equation. I put it at the top. P4O10 solid plus 6 PCl5 yields 10 Cl3PO gas. Okay, let me check, see if that's right, and that's right, and that's right. All right. So the question is, what is the delta H for that reaction? And we're given 4 reactions to work from. So where do you start? Well, you start with this equation, and you say, we need something that'll give us P4O10 on this side of the reaction. So we look at our choices. P4O10 is number 2. All right. Number 2 is reversed. So we need to flip that equation and put P4O10 on this side. Yields its reactants. P4 solid plus 5O2 gas And because we flipped the reaction, we made reactants into products and products into reactants, the delta H needs to be changed sign. So this would be delta H equals 2967.3. 2967.3 kilojoules. A positive. Okay, so we've used 2 now. How about PCl5? Do we have one that does PCl5? Well, yes. Equation number 3. PCl5 is on the wrong side. So if we put PCl5 on this side and PCl3 over here, PCl3 gas plus chlorine gas, correct? Yes. We change the sign. Now it's positive 84.2. But that's not the end of the story. Because now we only have one of these. We need 6 of them. So what we need is times 6. And that times 6 goes all the way through to the enthalpy. So now we have 6 here, 6 here, 6 here, and times 6 here. Okay, there we go. So we're going to use this one, and we're going to use this one so far. All right, now how about Cl3PO? Which one of those will do C3? The last one, number 4, Roman numeral 4 would be the last one. And it puts Cl3PO on this side, but there's only one of them. So if we put Cl3PO on this side, just like it is, and we have 1/2 oxygen, and PCl3 gas, we need to multiply the whole thing through by 10. Well, the value for this one is minus 285.7 for enthalpy. Minus 285.7 kilojoules. But we need to multiply the whole thing through by 10. So that makes this 10. That makes this 5. That makes this 10. And 10 times this is minus 2857 kilojoules. Okay. Now, we've got that one taken care of. We got this one taken care of. We got this one taken care of. And let's see, do we have any that cancel so far? Well, we have 5 oxygens here and 5 oxygens there. They cancel. Okay. We have 6 PCl3s over here. Yeah, 6 PCl3s and only 10 on this side. So what we need is 4 more PCl3s on this side. And if we use equation 1, we get those 4 PCl3s. And 1/2 O2. And, oh, excuse me. That's not right. 6 Cl2. 6 Cl2. And P4. This is equation 1. And the value, the enthalpy that goes with this one is minus 1225.6. Okay. So this one and these 2 cancel. P4 cancels here and here. 6 Cl2 cancels here and here. And what do we have left? Well, we already accounted for those, and we don't have anything lingering in here. This is covered. That's covered. All those are covered. So now that we have the correct combination of reactions, we can add the energies together. And we're going to use these four right here. So 2967.3 and 505.2 right here. And then minus 2857 and minus 1225.6. And that gives us the overall delta H of minus 610 kilojoules. Actually 610.1. But the answer is B. These problems take a lot of work, so you have to be very methodical about it. Start with your ending equation and look at the equations that you're given as your components and check them off one at a time using the rules. All right. If they're on the wrong side, you flip the equation and change the sign on your delta H. And then if you need more of them, you multiply the whole thing through by whatever factor, including the delta H. And then at the end, after you've canceled what you can, you see what's left over that's not supposed to be here. Then you look at your equations and see what's left available to add in to cancel those terms that you don't need. Keeping the delta H for those equations. Then you can add them together. And that's 59, and we're done for today.